We are learning about linear, quadratic, and exponential models. You're going to have to tell the difference between all these. So I know I've got this one. I can differentiate between linear, quadratic, and exponential functions, use linear, quadratic, and exponential models, and determine an appropriate function for modeling data. So some key vocabulary that you're going to learn is scatter plot, regression line, exponential function, natural base, and natural exponential function. Those last two aren't too important for right now. It's just kind of like a peek at what's coming in Algebra 2. So these are the different types of models. So you have a linear, a quadratic, and an exponential. So go ahead and pause and write all this down, especially draw the graphs. So how to determine which model to use. So linear, is y equals mx plus b, that's slope-intercept form. The first differences between y values are equal. So you're adding the same number each time when the x values are consistent. Quadratic is y equals ax squared plus bx plus c, and the second differences between y values are equal when the x values are consistent. Exponential is y equals a times b to the x. The first ratios are the same, or you're multiplying the same number to each y value when the x values are consistent. So this, if you get a chance, you need to go here and watch it. This is teaching you how to graph on Desmos.com. I'm going to do a little bit with you, but that will help you also. All right, so the first example says, look for a pattern in the table of values to determine which model best describes the data, and then write the equation that models the data. Okay, so remember, linear were the first differences are the same, quadratic second differences, and then exponential, you're multiplying the same thing. Okay, so let's look at our x values. They're going up by 1 each time, so they are consistent. Now my y values, what am I doing to each of my y values? I'm adding 2 to each of my y values, okay? So since these are all the same, since I'm adding the same thing each time, we're going to use a linear model. Okay, so which kind of model? We would say linear. And then what is the equation? All right, so your slope is going to be the number that you're adding each time. So all you have to look for is your y-intercept. Well, remember, your y-intercept is the y value where x equals 0. So it's right there. So your y value where x is 0 is 3. So that is the equation, and it's linear. And if you want to, you can plug some numbers in to see if it works, but it does. Okay, here's another one. Look for a pattern in the table of values to determine which kind of model best describes the data. All right, so let's look at these. This is, what are we doing each time? All the x's are consistent. You could say you're dividing by 3, but you're actually multiplying by 1/3. Do you see that? 4 times 1/3 is 4/3, times 1/3 is 4/9. So you're multiplying. So when you're multiplying the same thing each time, you're going to use an exponential model. So you're using an exponential model because you're multiplying by 1/3. Now, when you do this, the b is the number that you're multiplying each time, okay? So I'm going to have y equals something to the 1/3, times 1/3 to the x. Now, what is the a? The a is the y value when x is 0. So you're going to have y equals 4 times 1/3 to the x. Again, 1/3, the b is the number that you're multiplying each time, and the a is your y-intercept. Okay, what this is this is that value in Desmos. So I'm going to take you over here for a second, and I want to show you how to do this in Desmos, okay? So you're going to come up here, go to Desmos.com, push the plus button, and click Table, okay? And then you're going to add those numbers that were in the graph. Nope, we don't want that one. Okay, come up here. And then we had 36, 12, 4, 4/3, and 4/9. So you can see, look at the graph. You can see how it's working. Now, if you want to see the whole thing, push this button and it will show. Did you see what I did? I pushed, there was a little button over here and I pushed that. Rewind it if you need to. But you can see it looks like that exponential graph that we did. Now, if you come here and you type in the exponential model, you have to do a sub 1. Let's see. Equal, that means equals about a times b to the x, and then that x has to have a 1, and look, it'll graph it for you. And so if you see right here, look, this and this, they give you your values for a, so that would be y equals 4, and then 0.33 repeating is 1/3 to the x, and that is how you can get it using Desmos. Now let's go back to where we were. Okay. Let's try another one. Okay, look for a pattern. So I'm going to look for a pattern. Am I adding the same thing each time? So I'm adding 8. No, that's definitely not adding the same thing. And I'm not multiplying the same thing. So it's probably quadratic, but let's just check, okay? So from 9 to 17, I'm going up 8. From 17 to go to 33, I'm going up 16. From 33 to 57, I'm going up 24. And for 57 to 89, I'm going up 32. So the first differences aren't the same. So let me show you what I mean by second differences. From 8 to 16, there's 8. From 16 to 24, there's 8. From 24 to 32, there's 8. Since these are the same, those are the second differences, I know that this is a quadratic formula. Okay? So now we're going to go to Desmos again. Let's see. I'm going to exit for a second and go back to Desmos. Okay, I'm going to clear this out so I can show you how to do it one more time. Okay, so we go here, we add the table, and then I'm going to put 1, 2, 3, 4, 5. And then over here it's 9, 17, 33, 57, and 89. Okay, and then look, you see this button right here? Push it. And then it will show you what this looks like. Now, you really can't see that that looks like a parabola from right there because you don't see the other side going this way. But we know using our second differences that it is a quadratic formula. Okay, so you're going to put in the formula, the standard form of quadratic formula. So ax squared, hang on, I gotta see, okay, plus bx, again, always remember that sub 1, that's important, and then plus c. Do you see it? Now it looks like a parabola. Okay, and then you'll see these numbers right here. So let me write this down. So it's saying use a, b, and c. So y equals ax squared plus bx plus c. So then let's go back. And there you go. That is our formula because we said it's quadratic, right? It's quadratic. And then our equation we got from Desmos is right there. That was all the information, and there you go. All right, 1B, let's do this one. All right, what are we doing each time? What does it look like? Can you tell? We're multiplying 8 each time, so times 8 times 8 times 8, which means that it's an exponential function. And we're going to use y equals ab to the x. Now let's do this one without Desmos, okay? So the b is what we're multiplying each time. And the a is the y value where x equals 0. Or you can rewrite that just negative. Remember, the negative does not go on the inside. That would not make it the same. And there you go. Okay, 1C. Here, you go ahead and try this one. And you should have seen that it's quadratic, and to get the function formula you're going to use, to get the equation, I'm sorry, you're going to use Desmos, and you should have gotten y equals 3x squared. Okay, now we're going to determine an appropriate function for modeling data. So if the points lie on or near a line, it's going to be the linear. If it's increasing more and more rapidly, exponential. It's increasing, although rate of increase is slowing down, and logarithmic. We're not going to really use this one. This is for algebra 2, so we're not going to use that. Decreasing and then increasing is the quadratic function, or increasing and then decreasing is also the quadratic formula. So you remember from 10.4 that we graphed a parabola, and so the vertex is the highest or the lowest point. The axis of symmetry is the line going right down. If the leading coefficient is positive, it goes up. If it's negative, it opens downward. Now, something else, data presented in a visual form as sets of points is called a scatter plot. Y'all have done this before, a long time. A line that best fits the data points in a scattered plot is called the regression line, or line of regression, also called the best fit line. For example, the graph displays the relationship between literacy and child mortality. Each point represents a country. So you can see that as the percentage of adult females who are literate increases, the under 5 mortality death rate for children decreases. Definition of an exponential function, and you can see that y equals, they didn't put the a bx, but we know that's true. Okay, and so now we want to graph this. So how can we graph this? Well, I think that it would be best if y'all just did a table. And you could see, so let's start with plugging in numbers. Let's say at -2 and go to 2 and see what happens. Or even let's go to 3. Okay, so if I plugged in a -2, that would change it to 1 over 2 squared, which is 1/4. And then 2 to the -1 would change this to 1 over 2 to the first power, which is 1/2. Anything to the 0 power is 1. 2 to the 1 is just 2. 2 squared is 4, and 2 cubed is 8. Okay, so I'm just going to plot these points. So I've got 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. And so I've got -2 and 1/4, -1 and 1/2, just a little bit above that. 1. I'm just plotting, I'm just plotting these points. So I've got 1, 2, 2, 4, and 3, 8. So you can see that that line is an exponential function. Okay, example 3 says the graph below shows the world population for 7 selected years from 1950 through 2006. One is a bar graph and the other is a scattered plot. So they're showing the same kind of information, just with a bar graph and a scatter plot. Okay, so this next slide is on a graphing calculator, and y'all are going to use Desmos, so it's a little bit different. So it says after entering the data in a calculator, the graphing calculator displays the linear model and the exponential model. Express each model in function notation with numbers rounded to 3 decimal places. how well do the functions model the population in 2000. So what you would do, this would be similar to what you would see on Desmos, but you put, so the first one would be y equals, let's say, rounded to 3 decimal places. So 0.073 x plus b would be 2.316. And the exponential model would be 2.569 times b, which is 1.017 to the x. And so they want us to use those models to predict the population in 2000. So it says, by one projection, the world population is expected to reach 8 billion in the year 2026, which function serves as a better model. And so using the figure from the graphing calculator, the functions model world population in billions of years after 1949. The linear function is f and the exponential function is g. So you can see that. And then it shows you how they're done. The graph shows that world population 2000 was 6.1 billion. The year 2000 is 51 years after 1949. So we substitute 51 for x in each function and then compare the actual population in 2000. And you can see they're very similar. Since the world population was 6.1 billion, it seems both functions model the world population well for 2000. So we're trying to decide which function to use, either linear or exponential. So now we're going to compare the models to the world population of 8 billion in the year 2026. So we're going to use 77 for x, since 2026 is 77 years after 1949. So when you do that, you see the numbers are very different, but it seems that the linear function serves as a better model for projected world population because we knew there's going to be 8 billion in 2026, and this is a lot closer to 8 billion than that. Okay, and this is what I was saying about irrational numbers. They're symbolized by the letter E. It appears as a base in many exponential functions. It's also Euler's formula, Euler's number. This irrational number E is approximately 2.72, or more accurately, and you can read that. The number E is called the natural base. The function f of x equals e to the x is called the natural exponential function. So in this formula, all you have to do is plug the numbers in. That's all you have to do. So it says medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. The risk is modeled by this formula, where X is the blood alcohol concentration and R is given as a percent is the risk of having a car accident. In many states, it's illegal to drive with a blood alcohol concentration of 0.08 or greater. So what is the risk of an accident with blood alcohol concentration of 0.08? So all you have to do is you're going to take this number and plug it in for X in your calculator. So go ahead and do that. Pause the video. So you can see that's what you were supposed to do. And it says, putting this in the calculator, we get an approximation of that. Rounding to 1 decimal place, the risk of getting in a car accident is approximately 16.7% with a blood alcohol concentration of 0.08. So in this problem, you just have to know how to plug in numbers and put it in your calculator and understand what it means. All right, so here's some extra practice. You're going to create a scatter plot for the data in each table, and then use the shape of the scatter plot to determine if the data are best modeled by linear, exponential, or quadratic, and then write the function in function notation. You can also do this by using first differences and second differences. Okay, so the first one is quadratic, second is linear, and third is exponential, and you can see the functions below. So I know I've got this when I can differentiate between linear, quadratic, and exponential functions, use linear, quadratic, and exponential models, and determine an appropriate function for modeling data. but do you really understand? So describe how you can use the shape of a scatter plot to determine if a set of data is modeled by a linear function, an exponential function, or quadratic function. So if the data points lie on or near a line, the set of data is best modeled by a linear function. If the data are increasing more and more rapidly, the set is best modeled by exponential. And if the data points are decreasing, then increasing, or increasing and then decreasing, it's best modeled by a quadratic function. When would the scatter plot of the quadratic function not show increasing or decreasing, and what method would be best to use in this case? So when it only shows one side of the parabola, you're not going to see that nice U shape. So you need to look for second differences in the data.